So when we get to matrix groups, the statement was that we need matrices of determinant not equal to 0. Okay, that is the main point. Everything else is okay. So I'm very sorry, determinant not equal to 0. That is what we need. And so the overarching groups, biggest matrix groups are called GL and R and GL and C. Where the G just says general, that is as general as it can get, subject to only this condition, determinant not equal to 0. And L just means linear. N is the size of the matrices, n by n, and R means it is over reals. So it is over a real vector space, or we can for this say real entries and here it is complex number entries in the matrix. Now these groups, they have a natural carrier space on which they act. Is essentially n-dimensional, real or complex column vectors. That is the convention. We could have taken them to be row vectors, but column is the convention. And then the row vectors are called the dual, the row vectors are called the space dual to these. I didn't use this terminology so far, but and maybe we don't need it, so don't worry. But the row vectors are not the primary space, it is kind of a mirror image space of the column vectors. So this is the basic layout, and that is where one begins. And what one shows is, so what one shows is that there are a variety of subgroups of the general linear group which are of physical interest. So SON, SUN, etc., and also what are called symplectic groups, SP2N. So these are all various groups, they are all matrix groups. They are motivated by various physical considerations, and they are subgroups of the big matrix groups GL and R and GL and C, on whom the only restriction is determinant not equal to 0. So in fact we next go to one class of groups which are not very commonly used in physics, but they, at least one of them is used, and it is not any of the ones I listed, and that is called the special linear groups. The only restriction these put on the GL and R or GL and C is that the value of the determinant is +1. Okay, so here the requirement is determinant equal to 1. Restriction on corresponding GL So, earlier the determinant only was non-zero, but it could be any finite value or any value in the complex plane or real numbers. But now further we also require it to be determinant equal to +1. So, we will see that sometimes these groups are also interesting to consider, and in fact they are very useful even for the Lorentz group. Next, to talk about these groups SON, SUN, SP2N, it is useful to introduce the idea of a inner product. To introduce classical groups, notion of inner product on the carrier space. Which are some V, real or complex. Actually, it is worth knowing a particular abstract mathematics fact, that we tend to think of the vector space as real or complex by saying its components are real or complex. Okay. But in general, a vector is by itself not a number. So, the components is only a language in terms of which we think. So, in the abstract language, a vector space becomes real or complex depending on whether the scalar multiplication is by reals or complex. Okay. So, note that vector space has two algebraic structures. A plus for the vectors and a scalar multiplication. Or multiplication by scalars more correctly. Okay, let us write that because some so which is distributive over that plus. So, we have the property that if we have A times V1 plus V2, it becomes equal to A V1 plus A V2. It is also true that A plus B V is equal to AV plus BV. So, the scalar multiplication by scalar satisfies these properties. Okay, so sometimes in mathematics they generalize this set of scalars. So, scalars are typically either reals or complex. Now, the main thing that I was earlier saying, a vector space is called real or complex depending on whether the scalars are real or complex. What this means is you can have a vector space of dimension n. At this point I tell you nothing about whether it is multipliable by scalars or complex numbers. Then it just means that it has n basis vectors. Or vector space V is characterized by the fact that it admits n basis vectors. At this point these basis vectors are neither real nor complex, they are just basis. However, if I now say that the vector space is real, then so if the scalars are in R, then components of vectors relative to this basis are real. That is what this means. The components become real because you said the scalar multiplication is by reals. The same n dimensional vector space, if it is now, if I allow complex scalars, then if scalars are complex, then components become complex. But what this boils down to in practice is that secretly it becomes a 2n dimensional real vector space, because the complex numbers you can treat all the real multiplication separately and all the imaginary part multiplication separately. Thus n dimensional complex vector space in component notation is almost a 2n dimensional real vector space. So we just keep this in mind, but remember that it is not that the basis became complex, because vector space is a vector space. It is neither belonging to real numbers or complex. It is the scalar multiplication that makes it real or complex. Now we come to our inner product idea, and we discussed it already last time. It has those three properties of symmetric, bilinear and positive definite. Symmetric, bilinear and positive definite. And we have to add the rider, that when we come to special relativity, the Minkowski metric does not have the third property. In fact, so remember, positive definite means that x, the inner product of x with itself, equal to 0 only if x it's itself a 0 vector. So, I always emphasize this 0 is 0 vector, this 0 is the number 0, okay. But nobody bothers distinguishing them, but you should know that they are different. So, the positive definiteness idea is that it becomes 0 only if x itself is 0. But in Minkowski space, the direction of propagation of light or the energy momentum carried by light is a 0 magnitude Minkowski magnitude vector. The 4 vector of photons of massless particles has 0 magnitude but is non-zero. So, we will remember that distinction and carry it on later. I now wanted to go back to the two things that we wrote. One is algebraic form and one is geometric way of thinking. So, so we introduced ON is basically one that preserves the inner product, which in matrix language is X transpose O transpose O Y is same as X transpose X transpose Y. So, this requires that O transpose O equal to identity matrix of size n by n, and then SON additionally has determinant equal to 1. So, we checked last time that since O transpose O is equal to 1, the determinant has to be plus or minus 1. So, if you restrict yourself to plus 1, then you reject determinant equal to minus 1 members of elements of O, ON. There are two other ways of writing this out, which is one is a geometric way of thinking and the other is algebraic detailed way of writing. So, the algebraic or index notation we write OIJ O. So, I have to write O transpose. So, now I have to really be careful. What we will do is write O transpose IJ and then I have to multiply OJK, that is matrix multiplication, but that actually is same as O, and then we will put J here and I here, OJK equal to, so this is the transpose of that, but I remember that this index is up and this is down. This is what the slight complication is there because of the way we are dealing with this, and this notation is useful when we go to the Minkowski space. So, I will just define it like this, and so this should be equal to the identity matrix, which now becomes delta ik. For identity it actually does not matter where I and k go, but okay. So, this is index notation for stating the same thing, and then there is a geometric interpretation. So, we earlier defined inner product essentially algebraically, although we did not write any indices, we just gave the algebraic properties. It should be symmetric, bilinear, positive, definite. The geometric way of thinking about it is that I actually am defining a distance, a metric on the carrier space. And introduce a metric, a special matrix, I am sorry to say this, but that is what it is. So, the metric is the abstract notion, and matrix is of course one of the array matrices. So, introduce a special matrix which is, let us call it G in honor to Gauss, and because it has become standard notation. So, introduce special matrix G, and let us call it Gij, such that it is symmetric. Then Gij Vi Wj with summation over Ij is a general bilinear form, is called, okay. This is the one of the old nomenclatures. So, it is called general bilinear form, which is symmetric. And we also require that determinant of G is not 0, so that it does not have some null row or vector. So, such a Gij is called a metric in Gauss sense. And its geometric interpretation is that it actually kind of stretches and strains the vectors. So, let me write one more thing. The choice Gij equal to delta Ij is called Pythagorean. And is the simplest. In fact, if G as introduced is a symmetric matrix, a symmetric matrix can always be diagonalized, and a symmetric matrix, by transferring its diagonal whatever scales, that whatever eigenvalues there are, you rescale the basis vectors with inverse of square roots of those, you can make the matrix completely identity matrix. So, by G is symmetric real matrix, we can always diagonalize it. Also rescale the basis to convert it to Pythagorean. So in a sense the information content in both is quite similar or can be shifted back and forth between the choice of your basis and the choice of coefficients in G. Where it comes useful is where such a metric changes from one point in space to another. So for example, if you use say spherical polar coordinates, then the metric is r square 1 then r square and r sin theta squared whole squared. So if as a function of the coordinates the metric keeps changing, then this comes in useful. Thus the is either in G or in scaling and orientation. Of the basis. So now I have already made you accept what is geometric about it. It is actually just stretching and the angles between the basis vectors. Relative scaling and angles between basis vectors. So you might say what is the advantage, then always use Pythagorean, but the answer is that when G is defined on a space parameterized by some parameters, that is a repetition, but anyway, say u1, u2, u3, then reduction to Pythagorean may not be globally possible. Not possible as a continuous operation. If you want to do it as a continuous function, so the Pythagorean version, reduction to Pythagorean version is not possible globally as a smooth operation, smooth or continuous operation. So our simplest example is the curvilinear coordinates we use, but the curvilinear coordinates used in most physics problems like electromagnetism and so on are still such that the local frames are orthonormal. R theta phi also, the r cap vector, theta cap vector, phi cap vector are mutually orthogonal. that much we retain for simplicity, but when you get into more complicated spaces you may be forced to choose even more complicated metrics.